All right. So today we're going to discuss a last major convex optimization, pure convex optimization topic that we are going to study. It is semi-definite programming. Semi-definite programming is not the last in the pyramid, but it is quite on the top. So you can imagine you have least squares, LPs that can solve least squares, QPs that can solve LPs, QCQP further on, SOCP further on. Well, SDP, semi-definite programming, is on top of all of that. It can solve everything and include some problems that those don't include. Today we'll focus on what to do with this SDP. Next time, maybe we'll get a little bit into relations between SDP and other problems, more as an exercise. We'll see. Basically, I think with SDP, the main problem is conceptual. Like the way to use SDP is just, as simple as to use any other optimizations that you have seen so far. For example, using what do you call using QP. If you use CVX, it requires writing your QP, right? Using SDP just requires writing your SDP. You don't have to do anything else. It is just as simple. And you'll see programs that are like 20 lines of code today. But unlike QP, SDP doesn't have a intuition that comes from typical, undergrad algebra. So, and undergrad, I guess algebra, right? So QPs were based on quadratic forms and linear constraints. So did like LPs, etc. SDPs are, they're still quite close to ideas of linear algebra. Semi-definiteness is the algebraic property, right? You remember probably semi-definiteness as part of your linear algebra course. But big difference is, while it is algebraic property, it is difficult to visualize, and you definitely haven't tried to. I would imagine haven't tried to use semi-definite matrices as variables. You'll probably use them as coefficients. We'll go into it in a minute. So, although let me just, by the way, I didn't plug in my computer. Okay, I'll do it later. So let me just show you the difference about using them as variables. So let's say I ask you to do this. Minimize this function. Oh, the minimum is at 0, right? So let's say subject to constraints. Okay, QP, right? Here, S would be positive semi-definite matrix. Otherwise, you remember, we cannot solve this, right? It has to be positive semi-definite. That is something you have to remember already. All right. But that is coefficient, right? It's constant coefficient matrix. Okay. Now, if you remember Lyapunov equations, did you study Lyapunov equations in your linear control course? So for a system x dot equals to ax, what is the Lyapunov equation that can prove stability? A Lyapunov equation is Lyapunov function. It's no, not candidate Lyapunov function. I want the Lyapunov equation. It's a specific type of equation. Lyapunov function would indeed be quadratic. You are right. Let me write it for you. So you can write it. Unless I make a huge mistake, but hopefully I won't. Like this. Am I correct? I hope I'm correct. But if if I'm not correct, it will be switching. But we can derive of equation very easy. Should we derive it? Just for a recap on the what do you call it? Yeah, I do it on the linear algebra. Okay, how do we derive it? Well, we get a Lyapunov function. Lyapunov function candidate. Can I write here? I think at least I can write. So Lyapunov function candidate would be v equal to something like this. We know that for linear systems, Lyapunov functions would be quadratic. That is just a theorem that we take as given. Okay. What is the positive definite for asymptotic stability? So derivative of Lyapunov function would be derivative of function with respect to x times derivative of x, chain rule, right? So that is, by the way, this type of abuse of chain rule is actually what kind of leads to all kinds of troubles. This is the abuse of chain rule. Why? Well, because this guy is what? Oh, this guy is a function which is the multiplication of two functions of x, right? And by writing this way, you're kind of forgetting that this will become a sum. So this is a slight abuse of notation. At least it's not helpful. That's what I would say. Yeah. So what you can say is to be t xp dx x somehow times x dot, right? How can I multiply this by x dot? Well, you'll be smart to multiply it on the left. So that's, since we take derivative of this guy, well, our product will be a column vector. We'll multiply it on the left. Plus a x transpose e dx dx. And that, since we take derivative of this guy, our derivative will be a row vector, and we can multiply it on the right.
Sorry, Professor.
Yep, go.
Please excuse me, Professor.
Yes. Ask.
We can't see the right side of the board.
Oh, as usual, right?
Okay, thank you.
No. Please keep me in check about the variable. Thank you so much. So this sounds mysterious, right? And I do feel uneasy about those types of operations myself. But what you know for sure is this is a scalar, right? Derivative of a scalar is a vector, right? That makes sense. And derivative of with respect to vector, gradient we call it sometimes. If we want to just find this expression, we better find. We know from the rule of taking derivatives of a multiplication of two functions that we will have two functions that will sum. So we will have something like, f1 plus f2, and they better be the same dimensions. So if this is a row vector, this better be a row vector. If this is a column, this better be a column vector. That is one thing that you can keep in mind. That's sanity check, right? It just makes sense. Okay. Second, this is a scalar. No dimensionality exists here. So when you write something like this, you kind of know that this guy, whatever this is just going to be a constant. It's just going to be a matrix, right? And matrix times a column vector is a column vector. So this whole thing is a column vector. So you better multiply it by a row vector, right? Or If you don't like this notation, you could have just used dot product and just put a dot and say something dot something, regardless of dimensions. That is very nice, but not helpful for matrix operations sometimes. You need to be careful with it. And here, you know that this guy is just identity matrix. And this is a row vector. So row vector better multiplied by column vector. That is not have nothing to do with the subject. I'm just trying to make sure you're not super afraid of making those operations. All right, now. So what we get is x dot transpose p x plus x transpose p dot x. Now x dot is equal to ax. So let me rewrite it. X dot transpose a transpose p plus x transpose p a x. That is our p dot. Notice that this whole thing p dot better be less than or equal to 0 for asymptotic stability, less than or equal to 0. Non-strict. I believe it's non-strict for, or is it non-strict for? I think it is non-strict for stability in the sense of Lyapunov, right? For asymptotic, it should be strict, correct? I think so. All right. Anyway, good reminder to check on your stability definitions, right? So like very useful. Cannot check them all of them. All right. So this implies that this quadratic form. Let me rewrite it this way. By the way, did we guess it? Yeah, we did guess it, correct. This quadratic form better be negative semi-definite. So it's better be negative semi-definite, but it's going to be negative semi-definite for x plus u is only when this matrix is negative semi-definite. That's the definition. That's the definition of what quadratic form is. It's going to be negative semi-definite for all x, if and only if this matrix is negative semi-definite. Okay, so far so good, right? Also, P, notice that P here is symmetric. In fact, P is not just symmetric, it's also positive semi-definite. So this whole matrix has to be negative semi-definite. This P has to be positive semi-definite. So notice that this equation has constraint, which is a negative semi-definiteness. That is something we haven't seen before. And this variable has to be positive semi-definite. So the decision variable is a semi-definite matrix. Okay, can someone name me a random positive semi-definite matrix? Just in the exercise. Yeah, sorry if we are still on the type screen, but we'll go. Give me a positive semi-definite matrix. One, zero, zero. Yeah. Any diagonal matrix is positive elements of the diagonal is positive semi-definite. True. Now, non-diagonal positive semi-definite matrix. It's difficult, right? That's kind of like the point of the exercise. Want to show you it's difficult. Actually, the thing is, you have a matrix, a space of all matrices, and space of all positive semi-definite matrices has to oblige this rule, so they're symmetric. But also it has to oblige another rule. All eigenvalues of those matrices have to be real numbers and positive, right? So they have to be positive real numbers. And that is a very interesting requirement. I mean, the fact that they're positive slashes. I mean, if you think of eigenvalues as existing on complex plane, you slash like a 3/4 of every. So this is a constraint, but it's not a subspace constraint. This is a subspace constraint. This basically tells you have to exist in subspace, some sort. But this just tells you that out of everything that exists in this subspace, you can only take this quarter. Okay, makes sense? Right, good. And it is not easy to visualize this subspace. I mean, it is a cone, basically. It's some sort of a generalized cone. All right. So now that we got a feeling for what semi-definite matrices are, let me go forward with the presentation. All right. So what is a semi-definite? What is a semi-definite programming? Semi-definite program is in general is written as such linear cost. Don't be fooled by the fact that it's like linear. Obviously, you can go make quadratic costs by just introducing quadratic stuff. All right, subject to linear inequalities and semi-definite inequalities. What are those inequalities? Well, this inequality here is what? Well, it is a sum of semi-definite matrices, constant semi-definite matrices F and G. They are constant, multiplied by coefficients. So this suddenly doesn't seem so interesting, right? Before we were like, oh well, we can have semi-definite matrix as a variable, and now no, it's like semi-definite matrix is still just a constant. So it seems like a downer, but important part is you can construct your semi-definite matrices out of this procedure. So in fact, while it is written like this, you can still use semi-definite matrices as variables, and your solvers will understand it. And almost always when I use semi-definite programming, I use it on something like CVX. So I never need to worry about the form. It transforms it for me. And that's probably going to be your experience as well for quite a while. When you feel comfortable with SDP and want to write directly into the solvers, like in Groby or Mazek or SDP3, by then you won't mind those kind of things. So don't worry. It's like it looks strange, but basically it says you can use your semi-definite variables. Okay. Next, if you have two LMI constraints, you can combine them. How do you combine them? Oh, just write it as this combination, diagonal combination, and you get a new single SDP constraint, right? Is it clear? Any questions?
Yes, I have a question. Is there any difference between the symbol less than equal?
The symbol.
Usual, yeah.
Semi-definiteness. That means negative semi-definite.
Semi-definite what?
Of the whole thing. I mean, as usual, right? What does usual inequality? That means that everything that is here is smaller than the expression here is smaller than the expression here. Same way, semi-definiteness means that. Oh, I mean, let me just write. It's a good question. Right. So, what does this mean? It means that A is negative semi-definite matrix. Okay, that's clear, right? Okay, what does this mean? Does it mean that A is more negative semi-definite than B? Could have been the case, but it's not. It's not the definition. I mean, I'm not sure if you are correct on that, but the definition is not this. The definition is very simple. It's A minus B is negative. What this sign means is when you collect everything on the left-hand side, you'll get negative semi-definite something. When you correct everything on the right-hand side, you'll get positive semi-definite something. That's all. Right. By the way, is it true that if P is positive semi-definite, then minus P is, this implies that minus P is negative semi-definite? Is that true? Or is it not?
like proof. It's like proof.
Proof. No, I mean, come on. There is a proof that you can use. I'm not asking anything that is outside of the range of possibilities. Right? The proof comes from definition of semi-definiteness. Now, anyone wants to try? From definition? What's the definition? The definition is positive semi-definiteness implies that for any x p x is bigger or equal to 0. That's the definition. So how to prove from here proof this? How do you prove it?
We multiply by negative number of that.
Yeah, let's multiply it by negative number. If this is negative semi-definite, let's multiply. Okay, so let's just write it this way. Let's write that minus p is positive. Should I write? I'm trying to be elegant about it, but wait, okay, anyway, let's just write it this way now. Let's say minus p is negative semi-definite, okay? That implies this is less than or equal to 0, right? From definition again. It's correct? Now, minus p by the way. Well, we can push this minus sign out of the brackets. So minus x px less than or equal to 0. Can you still read it? No. Let me write it here. Minus x px less than or equal to 0. And that implies that x px bigger or equal to 0, which is exactly what we're operating here. So that's how we proved it. We just said that minus p is this negative semi-definite, then this is negative semi-definite, then you know, this has to be positive semi-definite. And all right, that is the way to prove this kind of stuff. And this is why this is equivalent to, when we say that those are equivalent statements. Okay, good. Now, hope I answered your question. Good. Now, as I said, sometimes it's easier to think about it in terms of SDP variables, like x is negative semi-definite, some function of x equal to 0. That is easier way to think about it. Let's go to examples. So far, very nice, but very abstract. Okay, example from what we just erased, we almost don't see the shadows. The only difference is now we have our equations before. 1 second, I will take a new marker. Now we have our equation in the form. Less than or equal to minus q. So we want this to be negative semi-definite. So if q is positive semi-definite, then being smaller than minus q would mean that this whole thing is definitely negative semi-definite, right? Because what the other, the other way to think about it is, if this guy is negative semi-definite, and this guy only makes it worse, right? It's like it's not helping. This is a constant matrix. It's not helping. It just makes things worse. If this guy is negative semi-definite, then this definitely is. Make sense? Right. So this is the way we think about it. Now, expression number 5 is the constraints for this whole thing. You can notice we have equalities constraints involving semi-definite variables. A and Q are constants. P is a variable. On the other hand, we can make Q a variable too, if you want to. And then the game would be find us a huge Q for which to still hold. So it would be find us a bigger margin of stability, kind of thing. What do you mean margin? Why Q is margin? So imagine A is slightly incorrect. If A is slightly incorrect, we will get expression here with an additional term, which would be error. Like you multiply this. I mean, do you see what I mean, or should I write it out? Let me write. Maybe this is the expression we have. And while this guy is negative semi-definite, this guy may not be. May not be negative semi-definite. But if this guy is smaller than this guy, yes. What should I do? Let me try to do this one. Do it this way. I'm slightly worried about messing up the whole setup. All right, now you can see it. There's the delta. So if this guy is actually smaller than this guy in terms of its semi-definiteness, so the sum of those two, the difference between those two is, so if Q minus this whole thing is still positive semi-definite, then you can hope. I mean, this does make a lot of sense because this guy doesn't have to be semi-definite at all. It can be not symmetric, but non-symmetric part is actually plays no role in quadratic forms. Non-symmetric part goes away; it always becomes 0. So, if symmetric part of this guy does not change the fact that this whole thing is positive semi-definite, then what will happen is in reality you don't have this matrix here. What you care about is that this guy or this guy is positive semi-definite, negative semi-definite, and since we know that this one is smaller than Q, then this whole thing would be still smaller than 0. That's that one. I'm not sure if I was clear. But basically, what this does is it lets you to have this matrix so small that it can compensate for a Q here. Well, that means that it would also be able to compensate for this component if it exists. That's the story. Of course, this is a hand waving. It's not math, right? So be aware. You cannot do math this way. You can just give your intuition this way. Math requires modification. Yeah. Come again?
Like you need a person. Yeah, like you don't help us. Like when you add this data, you don't help us.
So what you want is that this guy would be negative semi-definite.
Like,
No, what I'm saying is, as long as this is true, your system is stable. And you can achieve that by requiring this is true. Just choose such a big Q that it will going to be bigger than this expression. Make sense? So because this guy is going to be negative semi-definite from this expression. But it's not just negative semi-definite. It's going to have such a amount. What do you call it? It's going to have a what's a good word for it? Basically, it can take care of additional positive semi-definite components like this one. And how much of positive semi-definiteness it can take care of? This much. That's the step. All right, that's a typical approach. I didn't invent this Q to make it confusing. That is the standard way to write those equations. Always written this way. Good. Now you see the program 6. That is how you write this thing in as a SDP. Let's look at the code. So here's the code. Let me move the screen a little bit. Take a minute to look at it and give me your opinions. Notice it is a CVX code. So this is the program only takes between line 3 and line 9. And you probably cannot see those numerals here. But it's probably better for people who see it on the screen. But basically, the program is very simple. You define your P as a symmetric variable. You have no cost function and 2 constraints. Yes. Trying to find P. If you can find P, we can prove stability of the system. Then the system is stable with the margin Q.
P should also be positive semi-definite.
Yep.
It's also and last line the condition
Others. CVX can return you problem. Your problem being solved or being infeasible or having too many iterations, whatever. It doesn't have to have a solution, right? And you want to, if it does have a solution, status is going to be solved. That is the story. And if it is solved, you can just check that P that found is positive semi-definite, and this guy is negative semi-definite by looking at the eigenvalues. So maybe after we finish the slides, I will run some of those examples for you. No promises, but you definitely run them first. They are on the GitHub. All right. Now, next one. Discrete Lyapunov. What is discrete Lyapunov? Well, expression number 7 gives you the idea. How do we derive it? Well, let me just quickly derive it. Well, does anyone remember how to derive it? Discrete Lyapunov. If you want, anyone can go to the blackboard. Okay. Discrete dynamics is this guy. So this is discrete dynamics. Lyapunov candidate is same. But the requirements is that x I plus 1 minus x I should be less than or equal to 0, I believe. So this is difference equations. It's on differential equations, difference equation. So this is the condition of stability, discrete stability condition of stability, if I remember. So let's write. So what is vi plus 1? Oh, this xi plus 1. E xi plus 1, which is the same as right. You substitute here this on the right and the left. Good. Now, what is this guy? Oh, it is xi. It should be less than equal to 0. Let's write as a quadratic form. So here is your condition, and here is your discrete Lyapunov equation. Very easy to derive. You just remember that Lyapunov function has to go down as time goes on. In continuous case, derivative is negative. In discrete case, difference is negative. All right. So this is this thing here. Let it be negative semi-definite. And we write it as before, asking that this guy would be less than or equal to some minus q, where q is positive semi-definite matrix. And notice that I write it as minus q here, while on the slides we have something like this. Just switch between the signs, right? Another thing is here there is an inequality sign. There it is equality. Same stuff, same story. If you allow q to be decision variable, you can get away with what I've written in the equation 7 or program 8. But the program 8, I think, is incorrect. Yeah, program 8 is there's a mistake. Q should be a decision variable, I think, for the program 8. I think I'm not sure, but I think why. Or is it? Or is it? Now I'm confused. All right. Anyway, I'm not sure if it should be or shouldn't be decision variable. I think you can get away with maybe program 8. You can still get away with it. Maybe. Problem. You. I think you can. If it has let me give you my way of thinking about it. So I look at the slides, look at the program 8, and I think, is it correct or is it not correct? There is equality constraint there, right on the bottom of the slide. And I'm thinking, is it too tough? You can imagine out of all, the space of all matrices, only semi-definite matrices are going to be allowed there, right? And as we can clearly see, so it's like the big we're slicing some subspace there, but clearly from this formulation, all we need to do is to write inequality constraints. So basically, we can be equal to minus q, or we can be even smaller. just not bigger. So why do we slice? So essentially, you can think about it this way. Imagine that this is your decision space, and you say, okay, you should be smaller. This is a whole space that you're allowed to think. But on the slide, I say, no, place lie on this line where you're exactly equal to. That is a difference. Ask for everything that is smaller or for just something on the line. If you ask for equality here, it's probably easier to solve using Sylvester equation or something. I'm not sure how exactly Lyapunov is solved. I think it is solved using Sylvester equation. I mean, same as Sylvester equation, something like this. There is a very simple algebraic procedure to do it. And you can even imagine that this is a linear equation. So you can even solve it analytically. So sounds good, right? But it is equality, so we are lying on some subspace. Is that meaningful? Maybe, maybe not. If Q was a decision variable, it would have been the same as this scenario, because you can always make Q smaller, right? You can say Q bigger or equal to some Q0. Then it is the same as just saying that less than or equal to Q. So that is my line of thinking. But quite, maybe I'm just blanking out, and maybe it is okay. If it is okay, it means that for any Q, you should expect a solution. If this condition A is okay, then you have to expect a solution for this equation for any Q you choose. Because if one Q happens to be good enough so that you have a solution, then another Q have no business being not good. Either on average all Qs are okay, or on average you are never going to pick a good one, since we are talking about the equality constraints without any specifications, right? So okay, that is kind of like a mind games you can play with it. But better, of course, just look up at the literature and see the properties. All right. Good. By the way, next lecture we are going to study those kind of things, domains, and it will be very interesting, I think. All right. Here is how you write it as a SDP. See if you have any questions. Anyone can tell me why line number 12 and line number 14 exists separately? What do they want to do? Why did I write this if else? What's the difference between line 12 and line 14? Yep. Yep, exactly. I mean, it's going to be maybe equal to none or something. Doesn't make any sense to try to find its eigenvalues. Great. Very good. Why brackets? Why those brackets? I mean, it's just in case any of you are familiar with MATLAB syntax and can answer. Actually, for display, I wanted to display all of them as one on one line. So I merged into one vector. Okay, good.
Another question. I'm confused between P and Q. Which is
P.
What about Q?
Q here is a constant. And by the way, notice here is inequality. So, slide has equality, code has inequalities. What's going on? Q here is a constant. decision variables are defined explicitly. More questions? No? Okay. Now, this is, leap of complexity of like 3 stories high. So my apologies. So there exists, I want to give you a tool, but I don't want to dedicate a lecture to it. So instead, I will just give it in a very theatrical form. All right. So there exists something called finite time stability theory. Basically, it says, okay, let's say you want to go from point A to point B. Your initial position is approximately known. You know that you are inside some set. Let's say ellipsoid. You want your final position to be inside some set. Let's say ellipsoid. So you cannot know that your position, starting position is like here. Maybe it is here, maybe it's here, maybe it's here. Like you don't know. Your final position better be somewhere here. But you don't care if it's here or here, right? As long as it is approximately where you want. All right. But better be a small ellipsoid, right? Okay. This concept of going to a final set from the initial set is finite time stability. Now, writing Lyapunov equations for LTI systems can give you if you write them out, you can get for the system with control, you can get a very interesting equation where if you use a very interesting substitution, basically what you do is you let me let's say you write your Lyapunov equation in terms of S variable. I mean that I'm just giving you ideas, not derivations. You can make a substitution in this thing because P is positive semi-definite. You can do it. If you do this type of substitution, in terms of this new variable, you can write a very interesting condition. And that condition is this condition is something like a Lyapunov equation, except you have here new variables. L are it is interesting to describe. Let me try to describe it vaguely, but I think close enough to reality. So P here is ellipsoids. You can think about it as descriptions of ellipsoids. Okay, so this is your I think we often prefer to think about it in a slightly different way, but we like to describe evolution of ellipsoids, so the language is just nice. But anyway, let's say that this is your initial set. It's described by an ellipsoid P. And this is describing your control set. And so basically what you're saying is, for any element in this ellipsoid, we'll find an element in this ellipsoid that would make it stable. All right, so this is basically the idea. And what's the story about this whole thing? Well, the story is, you know that your control, so your basically your x are somehow in this ellipsoid P, and your u are somehow in this ellipsoid L. I'm writing it vaguely on purpose because we are skipping all the math, and sorry about that. But there is a book, Amata. You can read it. There's a chapter on this. It's good, but it would benefit from a long and careful reading. So here I'm just giving you the final piece. We have X somewhere in this ellipsoid, U somewhere in this ellipsoid. You know that K, like normally, U is equal to minus Kx, right? So you can say that maybe K can be found as by dividing U by X. So in this case, by dividing this ellipsoid script by this one. So basically, you are saying that maybe from this, follows that. Maybe from this follows this, and from this follows this. And indeed, that's true. It's not a derivation. It's just a hand waving here. But basically, there is this thing. If you describe your positions and you describe your controls that allow your this whole thing to be stable, you can then take back your control law from it. That is called explicit MPC. This idea called explicit MPC. I mean, explicit MPC is basically when you plan forward, and then as you plan forward, you try to see for a whole set of positions, what kind of set of controls you would get. And from that, you take back your feedback control gain. That is how in this formulation, it's this. Okay. Finite time stability. So this comes from finite time stability, this comes from the fact that we're trying to do explicit. You, if you are lucky, will get an extra lecture from one of our researchers who will give a whole lecture on different type of explicit MPC, maybe next week. It's going to be great, but difficult, more difficult than my lectures. So be prepared, but it's going to be good. Is a state-of-the-art material. All right, so. Like scary, don't know what it is, etc. Looks bad in all kinds of ways because you need to read the whole chapter in the book to understand it. But what is nice about it is in code, it looks just easy. And notice that program itself just got one more variable, which is not symmetric. And I mean, it's pretty easy. It's pretty easy code. And you can show that this matrix is going to be negative semi-definite. It's going to have negative eigenvalues. So you can show that this approach will give you a control. And you can do it steps ahead. You don't have to do it on one step like we did here. What you can do instead, and what we usually do, we write it on. Okay, so you can simulate it forward and get to your final position. And you can even change your A during this simulation. So your K matrix can change along the trajectory. That is how it becomes MPC. Okay, so it's going to be just as easy, just longer. Code is going to be longer. That's all. I mean, you can imagine you would have a four cycle and loop for loop, and you would have to loop from 0 to n, getting this expression. It's very easy. Understanding what is going on is quite a different matter. You would have to derive this one to understand what's going on here. And you would have to convince yourself that this whole rigmarole here makes any sense. It's actually going this here. I don't even want to attempt to try to convince you that it makes sense. But when we have a lecture on explicit MPC with polytopes, you will be probably convinced. Probably. With polytopes, it's much easier to discuss than with those guys. My personal opinion. All right. Good. That is a few examples of how to use it in control. Now, do we still have time? Tell me, how much?
20, 25.
Okay. Now, let me quickly go through ellipsoid geometry, which is based on SDP. We already saw it twice so far, so it's going to be easy. In terms of at least, it's not new. We already saw it. All right. So ellipsoid can be. So let's just see how we describe sphere. Sphere is a all points x such that x norm is less maybe to r. That's sphere. Expression 11, right? Very familiar. Or ellipsoid is just a linear transformation of a sphere, stretching and shifting, right? Stretching, rotation, shifting. So ellipsoid is notice there is absolutely no point in writing r here because we can get r here. Right? Cool. So ellipsoid is a unit sphere transformation. That is not just a definition, like it sounds like was it's so good, right? Mathematics define what is 3. 3 is 1 plus 1 plus 1. It's very profound. Move on. You get this feeling. A lot of mathematics is just definitions, like define what a derivative is with the limits and blah blah blah. This is unfortunate because it basically gives a wrong attitude towards some of the important definitions. Some of them are not constructive and some of them are constructive. This is a constructive definition. What do I mean constructive? What I mean is, let's say you in MATLAB, you can write the following. You use different brackets, you use brackets like this, and you write what does this do? Anyone knows? It will give you 3 arrays, 20 by 20. Each of them would contain points on the surface of this unit sphere. But those points will be in 3 batches. So this will be x coordinates of those points, y coordinates of those points, z coordinates of those points. If you want to plot the sphere, you would then call surf, which would do a surface. That's how it works. Why like this? Why not some other way? Well, because surfaces are extremely powerful in the sense that they are a 2-dimensional map of 3-dimensional objects. Okay, how do you get a ellipsoid? MATLAB doesn't have an ellipsoid function; it has only a sphere function. Oh, yep, but how? Yeah, what you can do is you can try to write it as a for loop. Let me write it here. Do we still here? You can write it as a for loop. Say let me write it maybe r equal to a x I j y I j z I j plus b. Then you say x I j r1, etc. you get the picture. So you can collect from each element of those matrices a vector multiplied by A, add B, and then put it back if you want, or something. So yeah, that's how you can do it if you want. Or much easier without formula is to do it this way. That's the way I would do it. You write, we still see. We can write, let's say, S equal to shape X. Then you write B equal to X double dot Y. So it's not double. What do you call it? Circle? Column. Then you write, you can actually write, say, B equal to A times X plus B. And then you say X is equal to a shape. The shape, I don't think it's quite right, but of the size. So, a shape. Yes. And the same here, whether we for Y it would be 2, for Z it would be 3. Right? That's how you can do it without formula. Much more elegant. What happens here? Save shape, turn it into a vector. They're going to be turned into the same. I mean, what's going to happen? They're going to be, I think the columns will be stacked like this. Right? Doesn't matter actually. Make them into row vectors. Create an array of points multiplied by A, then reshape back. Make sure you reshape exactly what you want to reshape. So rows. But very simple. Okay, good. That's why I'm saying it is constructive definition. Ellipsoid is a deformation of a sphere. That's how you actually work with it. You don't, sometimes you'll probably be tempted. How about I construct my ellipsoid or ellipse by like tangent of something like rotating, stretching, it's like, remember geometry from school and get some like wacky formula to do it with foci, focuses, remember, and other stuff. Would be good exercise, but I bet you this is faster. I mean, I don't know, but I just think it's faster. As long as this is for free. If you have this, it's probably faster. And you only need one of this guy. Then you can construct 1,000 ellipsoids by using different A matrices. So it's very fast. Right, good. Now we can introduce a change of variables. Let me introduce it. Let's introduce Z equal to AX plus B, right? Then X is going to be equal to A to the power minus 1 and A inverse Z minus B, right? Minus probably A inverse B. Is it correct? Yep, it's correct. So this one, the X is the Z. Now, let us rewrite this formula. Can you still hear it? The ellipsoid is Z for all Z plus C. So you can rewrite it in this way as long as your B is equal to A inverse, and as long as your C is equal to, can you still hear here? A minus 1. and minus, right? Minus. So with the change of variables, we actually managed to produce a different notation. Please notice this notation is no worse than the original one. It's a nice notation. The deformation happens not here, but here. The difference is here, the bigger A, the bigger the ellipsoid. Here, the bigger B, the smaller the ellipsoid. Why? Someone tell me why. Why is the bigger B the smaller the ellipsoid? Because of the inverse, right? That's one reason. Very good. Second reason. Second way to arrive to the same conclusion. There are another way. Okay, let me just give you the second way to arrive. You can say if B is huge, then Z would have to be very small to satisfy this, right? So, just by the virtue of B being huge, you will not be able to get very big Z. So it's going to be a very small ellipsoid. Okay, good. So two representations. They are very, very useful, both of them. Now, what is the volume of an ellipsoid? Well, the volume of ellipsoid, to compute it is a little bit difficult, probably. But to judge it is pretty easy. Determinant of A is proportional to the volume of ellipsoid in some way. Determinant of A in this representation, expression number 15. So if you want to maximize it, you'll have to maximize determinant. However, it's important to realize that maximizing determinant usually, you need to see if it is a convex function. Concave. You can only maximize concave functions. You cannot maximize convex functions. You can maximize concave functions. Okay. So maximizing volume of ellipsoid is the same as maximizing determinant of A. But that is the same as minimizing determinant of A inverse. Because determinant is a scalar. And we have this very nice flip that we can do. Determinant of inverse matrix is 1 over determinant of a matrix. 1 over the determinant of a matrix. So if it is strictly positive for positive semi-definite matrices. So basically A, positive semi-definite. B, positive semi-definite. Why? Well, because ellipsoids only make sense for positive semi-definite matrices. If you want, on your free time, try to construct this kind of set for other matrices. What will happen eventually? If it is like has negative eigenvalue, some of the elements will be, your sphere basically. Let me visualize it like this. So people can see. Imagine the sphere. When you deform it by positive semi-definite matrix, it happens. Stretches, rotates, etc. What happens if it is negative? Has negative eigenvalue? It's just going to flip. It's going to go through itself. And basically you would have maybe ellipsoid, but it's going to be equivalent to some deformation by positive semi-definite matrix. If it has complex eigenvalues, just try it, see what kind of geometry you would get. But my bet is it's not going to be an ellipsoid. Okay, try. So both of them are positive. So that means determinant is positive always. So 1 over determinant is also positive. If you want to increase determinant, you can decrease 1 over determinant because that's how fractions work, right? And that is a minimization problem that you can try to do. So minimizing something determinant is always okay. By the way, this makes perfect sense, right? Why? What is determinant? Is the volume of the span of the columns of the matrix, right? Do you remember this? It's probably have been. I mean, if you don't watch like 3 blue 1 brown or something, it's like like he has a very nice description of the determinant. Basically, volume of span. I mentioned this is a column, this is a column, and there's another column here. The volume will be like this trapezoid. Or if it is one column here, the volume will be area by spanned by this rectangle. Okay, so why is it convex function? Because you can decrease in any direction, and it's going to decrease, independently. But increase, that is not going to work. Imagine you have this function. You can increase this direction, it's going to increase like this, right? You can increase this direction, it's going to increase like this. But you can arrive at the same volume in both ways. So there exists 2 points for which the function has the same value. But in between them, the function has different values, and they are actually can be they can actually be bigger, I believe. I'm not sure if that is convincing. Let's, instead of trying to convince you in those, why should it be smaller? Just try to do it. Okay. Just write a 2 by 2 matrix and try to convince yourself that determinant of a changing columns independently would lead to basically would lead to this behavior. Let me write it. Would lead to this behavior. Just find 2 points on the yep. So yeah, try to do this way, like where you have here one matrix, another matrix, and show that determinant linear combinations of determinant small determinant of linear combinations. All right, just try it for 2 by 2 matrices. Okay, good. Sorry for failed attempts to visualize determinants. Sometimes I feel like it is clear, but when I start to explain, it's not. Sorry about that. All right, now almost there. Sorry about. I think we're almost out of time, right? But I would hurry up. So for ellipsoids of this form, ellipsoid 16, if we want to find bigger ellipsoids, we just need to minimize determinant of B. Why? Oh, because the determinant of B is determinant of A minus 1. So previous point, right? That is very useful. So we want to maximize volume, just minimize determinant of B. And by the way, if we want to minimize volume, we can get back to this representation and try to minimize determinant of A. So for minimization, use this representation. For maximization, use this representation. Sounds good so far. Now, let me open this link. So this is a lecture slides by Stephen Boyd, one of our main contributors in this field. Here is a description of how to solve a very specific problem. What is the problem? Find a smallest ellipsoid that covers the set. Let me write it here. So imagine you have a set of points. You want to find the smallest ellipsoid that contains. Smallest. So this means volume minimization. Volume minimization means we can minimize determinant of A. What do you mean by containing a set of points? Well, basically, what we need to happen is that every point here, let's call it Ri, should correspond to this like this kind of situation, right? So basically, we need what need to happen is that Ari. Is that correct? Yeah, RRI plus E should be less than 1. Is that correct? And at least that's what follows from the slides here, right? Oh, wait a second. No, sorry, I mislead the slides. Let me try not to mislead you. What we're going to use is this. Sorry about that. We're going to use this representation. Because with this representation, what's the problem is you cannot check if the point is inside this set or not, right? How do you check it? Here is very easy to check. This is the condition. As long as this condition is satisfied, all is good. So let's use this representation. So we just need to check that BRI plus C is less than or equal to 1 for this problem. But what is the cost function? Well, the cost function is we want to minimize, right? So we want to minimize the volume. If we minimize this guy, it's going to maximize this guy. So it's going to maximize the volume. So we want to minimize actually A, so B to the power minus 1. So we want to minimize E to the power minus 1, but determined. But actually, it turns out it's much easier to minimize logarithm of the determinant, not determinant. That's just how it is. Not going to go into details. So we actually minimize log. And there's actually one function. Good. Good. So this is how you do this kind of thing. And one last slide, I promise. Now you can do the same thing. Yes. Why is this then equal? Why 1? Where? In the constraint. Why is this then equal? Less than equal instead of less than. Why from this constraint? Because it's a description of ellipsoid. Our ellipsoid is described such that it will be 1. We can put any number here. It will just change B. Make sense? Can multiply, put 2 here and 2 here and 2 here, something like this. I don't want to be rash, but you can multiply both of sides by the same number. It's a convention. Good. Now,
sorry, Professor.
yes.
Could you? We can't see the side of the board.
Oh,
We can't see it clearly.
yeah.
Could fix the camera.
Yeah, let me try to move it slightly. Yep. I'll try to write carefully. All right, last problem. You have a polygon, and you want to have a ellipsoid inside this polygon. Okay. Largest possible ellipsoid. How do you find this? Well, first of all, turns out this time this representation is better. Why we will see in a bit, but maximum volume ellipsoid. In this case, basically means that we want to maximize A, right? So it will be max A, max. Which you have to ask yourself if it is convex. I hope just for the brevity, I'll probably drop this discussion for now, but you have to ask yourself that. Is the point. And then your polygon is described by equations in this form. well, linear inequalities. Okay, good. Now, let us write this in terms of this expression. So we want we put it here like that. Basically, what we want is that for any x, this would be still true. So what can we write? Well, we can say A transpose A x plus A transpose B less than or equal to, sorry, the B1 here is C1 less than or equal to C1 Ci. Okay. Now, and we know that x is less than or equal to 1. What is the worst case scenario? Like this is a constant. This is a constant. They're not going to do anything. The x set can give us trouble. What's the worst case scenario? Worst case scenario when this vector is aligned with this vector, because the length of this vector is limited. Yes. Hoped I would get a pause in the middle, so I would be able to plug it in. Thank you. So, so the worst case scenario is when this guy is aligned with this guy, because the length of this guy is fixed, but the direction can be changing. So, when are they aligned? Well, when x is equal to a transpose AI. Okay, let's write it. So what we have here is this part. What we have here is that this expression becomes something like A transpose A transpose A. However, there is one last problem that we need to tackle. X cannot be this. Why can't it? Well, for a very simple reason. It is a unit vector. So it can only be something like this. Normalized, right? So it will be divided by. But notice that this guy is nothing else but norm A. I mean, let me write. This is just a square, norm squared, right? By norm is a square root of the dot product, right? This is dot product. So this is the same as A transpose AI. Okay, so we can write it. This result here, and what we get norm of A transpose AI. Is it right? Let me just double check. What is D, by the way? Yeah, okay. This plus AI B less than equal to C. Okay. So what are the decision variables? Decision variable is A, decision variable is B. So we can choose A and B, that I described in ellipsoid, the way we want. And this is a little questionable still. You know, you would have to be sure that you can put your semi-definite variables inside your, inside the norm, and you would have to do some changes there, basically. This is linear. If you remember, this is the same as we did in Chebyshev, center of polyhedron. But scene transformation. So okay, let me stop here. Oh, yep. Let me stop here. I leave you with this one, the question here. You can read more. This is a topic, huge one, in research. I mean, how to solve it is very easy. How to use it is a very huge topic because possibilities are enormous. A lot of state-of-the-art software that had been developed the last 10 years was based specifically on this. If you want to, and software in, for example, path planning for mobile vehicles. So one of the best algorithms were developed there. And theoretical, analytical geometry or numeric geometry. So pure mathematics also uses this kind of thing often enough. So here you touch state-of-the-art basically. But notice, previous example was very clean. This one is not very clean. So same as with the MPC that we discussed earlier. It wasn't very clean. And we don't have time to go into details for all of them. But I hope you see the possibilities. With SDP, you today learned, easy solving Lyapunov equations. Nothing new. You can solve Lyapunov with anything, but also explicit MPC. You need to read Agata, I believe, the writer, the author's name, to be able to understand what's going on. But you can read it. There is nothing scary there. Go ahead, and you acquire a unique skill. This step from Stephen Boyd. Read up his textbook. It's free, I believe. I mean, it is available as a PDF everywhere. And probably is free, I would imagine. Though it was published by, by a publishing company. I don't know what's the legal status of it, but his lectures are free for sure. You can read on it, and you acquire a different skill in path planning and geometry. That is a kind of stage where now a lot of your knowledge acquisition will depend on the amount of work you put in. Okay, next lecture we'll discuss a little bit about domains in the much more in-depth way than what we did last time, in terms of, and we'll try to understand what's going on with under the hood of the solvers a little bit, and maybe we'll do a little bit of practice. Okay, that's it. Sorry for taking so long today. And thank you. I'll stop the recording. You can ask questions.